GCM, or more recently called Earth System Model, ESM, and the latest is a coupled model into comparison 5. And when you use this kind of models, and you have a problem for Hawaii because their resolution is pretty coarse, 100 to 200 kilometers. And you know that islands in Hawaii are very small, 50 kilometers, except for the big island. It's a complex terrain. You have the mountains, you have the valleys, so on, in different landscape. So in other words, for example, microclimate in Oahu cannot be represented by a couple of models. In other words, by this kind of models, and necessary to downscale the model output through statistical or dynamical approach. So to obtain local knowledge of future climate change. So this will provide water agencies or researchers with the information such as rainfall, evaporation, wind speed, or whatever, or solar radiation needed to plan and prepare for these future changes. Okay, let me just say something about the statistical downscaling. First, the idea is to find an empirical relationship between large-scale atmospheric conditions, like we call it predictors, such as the wind, humidity, sea level pressure, and so on, and the small-scale variables we call it predictant. In this case, it's the rainfall, because this is what we are concerned about. Using some kind of statistical method. So this is the essence of statistical downscaling. And for Oahu, I pick up Oahu as a case study that we use the historical rainfall data over the last 30 years. Also the NSAP reanalysis data for the current climate condition, and also the GCM simulations to project future changes in precipitation extreme. So we define precipitation extreme as those exceed the 90th percentile of daily rainfall distribution. So in other words, it's a heavy rainfall event. And when you come to reality that looking for rainfall data that we needed to, because for the statistical analysis, you need the sample size to be large for the result to be stable. So we choose at least 30 years of daily data. And then we apply a 3 to 5 rule for selecting stations. So if we have 3 consecutive days are missing in the particular month, then that month is tossed out. Or 5 non-consecutive days are missing, then the month is removed. So originally we have something like 60 stations for Oahu, but then this dropped down to only 7 stations. And this shows the location of these 7 stations: Campbell, Honolulu Observatory, Airport, Punchbowl, and Pecos Drive. So these are 5 stations are located on the leeward side, mainly along the coast, except for Punchbowl. And we have 2 stations on the windward side, Polygon and Honolulu. But later on, we found that the result for these 2 windward stations are not very good, so that I will be only showing results from these 5 stations. So come to the predictor selections, we use the 2 methods. One is just a simple Pearson correlation, another one is rank correlation. And the period used is last 30 years. So suggest the 4 predictors are reasonably good. The relative humidity at low level, zonal wind at the low level, meridional wind at low level, and also sea level pressure. Those 4 predictors are important. And usually people do this kind of statistical downscaling. They use a linear method. But when we concerned about the rainfall extreme, because we're looking at this heavy rainfall event, and their changes do not respond linearly to atmospheric forcing. So in this case, we use a nonlinear neural network method. So it has advantages, including extracting maximal relationship between predictors and also the desired response. So I'm not going to go through this detail about the neural network. But just say that we analyzed 24 GCM and also their emission scenarios. And we try to determine which model is the best to use because we don't have resources to analyze all 24 models separately, individually. Also, we don't have time. So we used some approach suggested by IPCC is that they have two tests. First one is they call the baseline test. Okay? In other words, you use a historical with GCM data to see how they compare. And here we use absolute difference as a measure. So that we also assume GCM that most accurately represent the rainfall is also the most adequate model considering the rainfall-related circulation features. So among these 24 models that ACAM5, oops, some blocks here. Shows a relatively small difference. Of course, you want this difference to be as small as possible. Right? So this is the first test. When you have your observations, then you can compare the models with observations. And the second test is to look at future projections. So in this case, we don't have any observations, so you cannot compare with the observations. So you just need to compare models with themselves. Right? So how does model compare with other models for future projection? So models with outlier projections are rejected. So in other words, that if the model shows values greater than 1 standard deviations, then they are discarded. Okay? And you just keep those within 1 standard deviation, just treat them as a consensus. Okay? And then rank them according to the absolute difference from the mean of the model. Example is that these two tests are then combined to find an overall high-ranked model among all 24. Okay. So in this case, based on the first test, baseline approach, for example, ACAM4 is not the best, but it's the fourth best model because the absolute difference is the fourth smallest. And based on the test 2, ACAM5 also is not the best, but it's the eighth best. But if you combine these two, it is rank. Rank is 12, which is the highest rank among all the comparisons. Okay. So in this case, we choose ACAM5. And this shows the result. Okay. Okay. So let's use the Honolulu International Airport as an example. Okay. So during 1979 to 2008, 47 high rainfall events are observed. So this is the actual observations. Okay. And there is 95% confidence that this true value lies between 36 to 63, so based on the bootstrap sampling method. Okay. And then for the same period as the actual observation, so this is from the GCM. Okay. And also the same threshold for defining heavy rainfall event. That 43 heavy rainfall events were observed from the model, so this slightly underestimate compared to the actual observations. And for the next 30 years, that the model projects 59 heavy rainfall events. So this is higher than the past 30 years. And actually, the same result also applies to other 4 stations. For example, like Campbell, according to the actual observations, you had a 41 event during the last 30 years. But now, for the next 30 years, you have a 50. For Honolulu Observatory, from 51 to 53, almost the same, slightly more. Echo from 62 to 68, Punchbowl from 58 to 64. So we do see more heavy rainfall events projected in the future. And in terms of rainfall intensity, that current rainfall intensity for Honolulu Airport is about 79 millimeter per day. It's about 3 inches. Okay. So this is the 90th percentile. And from the model, for the same period, it drops to 71. Okay. So rainfall becomes less intense from the model. The model shows some kind of drive bias. And for the next 30 years, the model shows even lower rainfall intensity, only drop to 66. Okay. So the same result also is presented for other stations. So the, oh yeah, okay. Then I will lump all the result from dynamical and statistical downscaling together in the last part. Okay. So now move to the dynamical downscaling. What is the dynamical downscaling? And this is achieved using high-resolution regional climate model that is initialized with output from GCM or Earth system model. And the weather research and forecasting as the WRRC model developed by NCAR has become the standard regional climate model. Okay. And the advantages of dynamical downscaling is that it is physically based, high resolution. In this case, we use the resolution 1.1 kilometer in numerical simulation. So this can be used because it's high resolution. So you can use this model result to any locations, even in the area where groundwater recharge is highest. This usually occurs on the mountains. There's no observation. And the GCM output also can be used to drive small-scale hydrological model within the watershed. So you can study the hydrology within the watershed. But of course, there is a price you have to pay for it. Okay. There's a heavy computation demand because of complexity of model physics, different data format from the model, from the data, and now you have long integrations because you deal with the climate change and high resolution and also nesting. So the model physics for the WRRC is that you have a long wave, short wave radiation, you have a boundary layer, you have a cumulus parameterization, cloud microphysics, you have land surface models, and also you need to modify land surface data because the official WRRC release gives you very crude values. For example, for the land cover, they only has urban and also mixed forest in Hawaii, but in reality, USGS classified into 24 types instead of 2. So you need to revise the official release. And this shows the modeling system flow chart. So on the left, you have this WRRC pre-processing system. Here is a model, WRRC model. Here is post-processing visualization. Okay. And in the pre-processing, a suite of programs is used to prepare this terrestrial data and also meteorological data for use in the WRRC model. This is the advanced research WRRC. And on the left, you have this external data source. For example, you have a conventional observation data like a rain gauge. It's located at a regular location. You have alternative observational data like a satellite data over the oceans. And here you have a terrestrial data. You have a graded data from the models. Okay. So they are coming to the models. Okay, based on pre-processing. And you have this raw output from the WRRC cannot be read by users. So this means that other program must be used to read the WRRC output. And the most common one is the GRASS and also NCL. So here it shows the domain we used. We used 4 different domains. The parent domain is 30 kilometers, which is not shown here. Okay. Resolution is 30 kilometers. And then this is the resolution for 10 kilometers, and down to 3.3 kilometers, and eventually down to 1 kilometer resolution. So this shows one result for the March 2006 flooding. As I mentioned before, many areas will received something like 500–600% of average March rainfall. So this one shows that we have a very high rainfall, even more than 1,000 millimeters. This is more than 40 inches on Kula Range, and also extending it to here, it's about 500 millimeters. And then even in the valley, usually where it's very dry, you have more than 10 inches of rainfall in March 2006. And for Kauai, it is even more so that we do see you have here is more than 2,000 millimeters. So this is like 80 inches of rain, lots of rain here. And also the wind, usually, you know, in Hawaii, the wind is coming from northeast, right? But in this particular month, we don't see northeast trade. Instead, we see some kind of southeasterly wind here. So this brings the moisture from the lower latitude to the island. So here, summary for part 5 is that for the statistical downscaling, it shows that for the next 30 years, the frequency of heavy rainfall event will increase, but their mean intensity will decrease on Meteorology. And also, dynamical downscaling based on the WRRC shows that it can simulate rather realistic rainfall distribution and amounts from March to 2006. But the rainfall, the simulated rainfall we compare with few stations shows simulated rainfall is still below the actual observation. So we need to do more verification. And also simulating the surface wind for this month southeasterly to the east of Kauai, so bring moisture to the island. So this is very different. And now the work is in progress that after we done this, checking of the past of the current climate conditions, we want to move into the future, hopefully next 50 years or longer, using the dynamical downscaling approach. And this shows the relevant publications, so that just for your information, that so we're looking, basically we're looking rainfall, Niño, interannual, interdecadal rainfall, and also extreme rainfall patterns, and then rainfall changes in terms of the climate change indices, and also looking at the statistical downscaling approach. Okay, I thank you for your attendance.
Sure.
Yeah.
The statistical downscaling part, you say that's extremely dense, and you needed to apply non-parametric solutions as there is no linearity. So if you have mean rainfall, in that case, can we apply linear relationship?
Yeah, I think if you have a mean rainfall, probably you're talking about not daily, right? You're talking about a seasonal.
Maybe monthly.
Monthly, I don't know. You need to look at the distribution of data. If the distribution shows a very skewed pattern, then probably the linear method is still not very good.
Still not very good.
Yeah, it depends on the data itself. So I don't know. If you deal with the seasonal, probably it would be better. Because when the daily rainfall is very skewed, it cannot be described by the Gaussian distribution. It's not like a Ghana distribution. And if you have a monthly, so you sum up 30 daily, asymmetric distribution, maybe they become a little bit better, but they're still probably not this bell-shaped symmetric distribution.
Thank you.
Question about
Yeah.
connection to PDO, and so my understanding is in the positive PDO phase, you have less rainfall.
Right.
Okay. So now you also, at one point, you also showed there's a trend since 1980.
Yeah.
There's a big, but if you think of what happened to PDO is that actually right now you have it really in the negative phase.
Mm-hmm.
So those two do not match. So what happened?
Right. So actually the PDO, because the time period is very long, so this study is only based on the one PDO cycle, one positive PDO, one negative PDO. Okay. So in other words, we didn't look what happened in most recent maybe 5 or 10 years, okay, because many of the PDO was in the negative.
So when you do this composite, how long is the data? I mean, from what?
Yeah, we looked at the data for the PDO was from 1950 to 70s, one PDO cycle, and another cycle. So it's, each one is about maybe 25 years,
Okay.
approximately.
Maybe it's a philosophical question.
Yeah.
So ultimately, I mean, I understand, you have PDO, ENSO, these are well-known climate indices, great. But on the other hand, the rainfall ultimately is dependent on the local atmospheric condition.
Yeah.
So aren't you better off to use an index that's based on local wind or vertical velocity rather than PDO, for example?
So basically, I always, very puzzled about the influence of PDO on rainfall. I'm more inclined to believe that El Niño, La Niña with rainfall, but not so much on PDO. Because first is that the rainfall change with PDO is relatively small compared to El Niño. And also second is that here because PDO cycle is very long, and all observational data is not that long, so we can only get one PDO cycle, positive, negative phase. So based on one PDO cycle, actually, there's a lot of uncertainty.
Yeah.
So I personally don't like the PDO cell, but what can you do with this?
But it's kind of interesting. Ultimately, you show, with regard to the PDO connection, you show it's just the reduction of the trade wind.
Yeah.
So if that is the case, I just thought, maybe using the trade wind intensity may be better.
Yeah. That's another way we can go.
That's very interesting there. Thanks.
I was going to just ask you this after, but I might as well ask you this now. I don't mean to take up anyone's time, but I also do statistical analysis on winds and waves.
Yeah.
And so I'm kind of curious of your methods. One of the questions I had was, what type of FT distribution do you use for your GEV statistical analysis, FT1, FT2, FT3? And then also I had another question about what agency provided the rainfall measurements in your study?
For rainfall measurement, we use data provided by Manoa. So actually, those kind of data are available in the public domain.
Isn't it USGS?
No, we go to the
Manoa, right?
Manoa, that's the NCDC, National Climatic Data Center.
And then how about the FT distribution?
What is the ST distribution?
FT, but your statistical, your GEV
Yeah.
distribution,
Yeah.
there's three types.
Yeah. No, we're talking about this GEV, so that's generalized extreme value distribution. Yeah, so it has three parameters. So usually people use Gumbel distribution, which has only two parameters. But in this case, that when you have three parameters, GEV, when the shape parameter becomes approaches zero, and this is the Gumbel distribution. So you can think that this is a more extended distribution.
Did you try the others, and did the way you use get better results?
No, we didn't use the other because the GEV in meteorology community becomes almost like a standard extreme value distribution. And so I didn't use any others. Okay. But I don't know. I think that you are welcome to use a different distribution to see if there's a difference. So probably I would think that the difference should be very small.
Yeah, very small. I used GEV as well as Gumbel too. Very similar.
Very similar?
I usually use Gumbel myself.
Yeah, because I know Gumbel distribution sometimes is underestimated when you have a very large value. Right? So you have to be more cautious about using the Gumbel distribution.
And then the third question I had, have you investigated how extratropical storms have affected the Hawaii rainfall?
Extratropical storm, that's a good question. No. I don't know. Why would you think that they have some influence?
Generally, in the Gulf of Alaska region, but they affect wave action. So I'm thinking maybe they might have some.
Okay, because our understanding for the synoptic forcing which influence rainfall in Hawaii is based on several factors, like corner storms, okay, or you have some kind of upper level trough, upper level lows, okay, and also if you have this front, okay, like cold front moving into the island, which also brings rainfall. Okay. Summertime you have hurricanes, but then ordinary you have the trade wind. So those are the major factors, and they are not in the extratropical regions. Because corner storm is mainly in the subtropical region. So that's the reason we didn't explore what happened in the extratropical.
Okay, from what I've seen, the trade winds affect the wind seas, and then the swells, the waves are affected by the extratropical storms. And I thought maybe, I was wondering how extratropical storms would affect rainfall.
Well, in one of your slides, when you choose your GCM from the available 24 GCMs, you look at the absolute difference between the historical and the GCM values.
Right.
The absolute mean difference?
We're looking at the absolute, mean difference.
Mean difference. But you're interested in extreme difference, which is 90%.
Yeah.
Or would you look into the mean difference then?
But that's probably that's a lazy approach. Yeah, you are right that more rigorously, one should be looking at extreme rainfall statistics instead of just looking daily difference.
Daily mean value.
Daily mean value.
So that will actually add a bias into your.
I thought about that afterward, okay, because after we did this then. So, oh my gosh, maybe we should do that, but unfortunately the students left. It's very difficult to continue.
Okay, so basically, did you look at quantiles of the historical observation, like from the station, with the historical GCM values, like to compare the quantiles of the students?
Not so much. We looked casually, not really systematically, looking at the quantile difference. Yeah.
So basically, the stationary assumption is built into your.
Yeah. So basically, this is like a quick way, maybe quick and dirty way.
Okay.
Yeah. But of course, there's a room for improvement. But that's good.
Well, question, you mentioned we are, as hydrologists, we are interested in spatial distribution. Basically, like estimating recharge.
Okay.
Normally, that's an issue.
Yeah.
So it looks like the statistical approach is not really very useful here in Hawaii.
Yeah, I think the statistical downscaling approach is limited by several factors. First is that you need to have a station with a long-term record. And then, usually in Hawaii, it's very difficult. And then the second is that hopefully that you have data which is complete. There's not much missing. If you have a missing, particularly in the crucial period, like a winter, then you have some problem. And also statistical approach that rainfall, you can only estimate rainfall. You cannot estimate some other variable, which is like a dynamical downscaling. You have a model, so model can provide a suite of other variables, like a wind, not only rainfall, but evaporations, wind, and whatever, solar radiations, and so on.
But also for the dynamical approach, we really would care much about uncertainty because you agree that there's lots of uncertainty.
That's right. I definitely see there's a lot of uncertainty that for the future projections, because each model will give you, some different pictures about the future. So how do you, reduce this kind of uncertainty? I think would be the major work.
And if you talk about extensive calculations, that's
and then you need to find some metric to represent this kind of uncertainty.
What are the most influential parameters that affect the modeling?
Oh, that's a very good question. I think that we just recently tried to explore what is the most important factor. I think one important factor is about the forcing field. In other words, this kind of regional climate model is forced by the GCM. So how do you define your outer boundary for forcing? If the boundary is too small, you cannot capture important synoptic activities affecting rainfall. If the domain is too large, then probably mix so many different synoptic activities, which may some activity may not be relevant to rainfall in Hawaii. So there's this kind of a trade-off we have to try with a different forcing field. And then maybe some cloud microphysics also may be important.
Maybe one more question. I guess some people even think that it is a two-way street, like you cannot really predict climate change based on existing conditions. Actually, the condition will change on land,
yes.
so that would affect climate change, as I mean, affects the predictions. So it is more like, yeah, climate change will affect the ecology and land covers, things like that, and vice versa. So we have even more complicated situation.
Yeah, and also I think that even with this very complicated GCM or ESM projection, I'm not sure they really incorporate like Greenland ice sheet melting or ice melting.
So these are not accounted.
Probably not in the model. Yeah, because who knows? Nobody knows. It's very hard to say. So there's a lot of uncertainty. But regardless of that, with the current information we have, we still need to provide information to the living water agencies. Right? They need to know this. Okay? They just say, based on what we already know here, published or unpublished, that what your model can tell us.
But as I can see, they are interested in even shorter terms, like they're thinking about 30 years, not the
Oh, really?
century.
You think 30 years?
I mean, you showed
No, I showed it for the next 50 years.
Oh.
50 years, yeah. But of course, if you have unlimited, supercomputer resources, you can use 100 years simulation. That's also can be done. But here, working at a university, that you actually doesn't even have a supercomputer. We used to have a supercomputer, but we don't have a supercomputer anymore. So we have to beg some agencies to give us some limited free time to use the supercomputer. Then they say, we give you just a few hours. Okay. Then it's going to be sometimes you got to be very clever about how you use your limited resources for the climate change simulation, because of the simulation time usually is just a few minutes, few seconds. Then you have to think about 10 years, 20 years, 30 years. A lot of computation time. And sometimes your simulation is wrong, and you have to repeat it again.
Okay, all right. One more question?